Well, just to start off the class, I found out what the collective term for students is.
Uh-huh.
And, class is an organization, so class is properly categorize just any random group of students.
Yeah.
Just like you have a herd of elephants or something.
Yeah.
A collection of students is a flunk of students.
A flunk?
Yes.
How'd that come about? That's weird.
Yeah, it's weird. But isn't it awesome?
Is that where the term came from? That's
no, actually.
I mean, is there a connection between flunking meaning failing?
Oh yeah, there most definitely is. Like most collective nouns in English, there is an association between a common attribute and.
Well, I'm sure it's very common in Math 101. Okay. Well, speaking of teaching horror stories, you have a test. So well, okay. So I had a little quandary going into Monday's class because by then I'd looked them over and seen where people went wrong, and several problems, especially like the last few problems, people seem to be in pretty good shape. I thought, well, if you take things to its logical extreme, there's a certain amount of, so given sufficiently long time, probably everybody can get 100, which from a teacher standpoint, I wouldn't really want that because you want to have some measure of who knows this material better than others. And I was actually concerned that at the rate you guys are progressing through problems, whatever time I give you on Monday, that might lead to everybody getting 100. That did not happen. I guess, and admittedly, I was disappointed as a whole, collectively, that more wasn't done with whatever feedback I gave. So some will be happy, some will be less happy.
Well, that is the most polite middle finger I've ever heard in my entire life.
Okay. Well, the average was an 87. So keep that in mind as you see what you got.
Yeah, sorry, we didn't make progress.
There is that. Yeah. And then I will take some time to go over these. So, admittedly, those first few problems seem to cause some difficulty. So, the idea is to what I was hoping for. So problem one, showing that the sequence of functions converge to 0 in L2 didn't really pose much trouble. It's basically just working out an integral. It was after that the fun began. So you have fn of t equals n to the minus t converging to 0 in L2, 0, 1. So what about pointwise or uniform convergence? Well, the thing to do is you can settle the question of pointwise or uniform convergence quite quickly. Because keep in mind, we're looking at any t between 0 and 1, including 0 and 1. Let t equal 0. What is fn of t equal to then? What? 1. So it's not going to 0, ever. It will never get there. It'll stay at 1. So at any other point in the interval, it'll eventually get to 0. So what happens is, if fn of 0 for any n is equal to 1, game over. Then you're not going to see pointwise convergence. If there's not pointwise convergence, there can definitely not be uniform convergence. Now, whether you choose to try to explain this in terms of the epsilon definition or not, that's really the crux of the argument right there. That if you can find the easiest way to show lack of pointwise convergence is to find a particular t at which convergence simply doesn't happen. A lot of people went for t equals 1, which was a good idea in other examples, but not this one. Generally a good idea to look at extremal values in your domain, because if something's going to go wrong, chances are that's what's going to happen. But you got to look at both extremes, not just because if you look at the t equal 1, you get 1 over n. In a pointwise sense, that's still going to 0. Okay, so yeah, so I was hoping more people would at least look at this, like look at the side of the domain. Okay, so all right, so that was the story with first one. Second one, dealing with the bilinear form that is an inner product on the reals, but not for complex. So you end up showing that in the real case, or really whatever you have, I'm going to have a correct expression here. Right. So you end up with 2v1 squared plus v1 minus 2v2 squared. As a sum of squares, you can definitely say, if v1 and v2 are real, you can definitely say that this is greater than or equal to 0. We'll talk about complex in a minute. So, okay. Now, what the key thing to focus on that needs some more attention is you need to show that the only time that this whole expression can be equal to 0 is if v1 and v2 themselves are 0. So the easiest way to show that is you focus on each square individually. So, so if VV equals 0, then the individual squares must be 0. And in other words, what is being squared is equal to 0. So you use the first one to say, oh, V1 is 0 right off the bat. Then you substitute that into here, and that means V2 must also be 0. So that's the idea. When sum of squares, each square must be 0 if you're given it the whole sum of squares must be 0. So that's the easiest way to see. Oh, now it's not the only way to do this. Right? You look at, like for instance, you look at the different cases. Like what if V1 is positive, V2 negative? Different combinations that can work too. But so I give you quick and dirty ways to prove things.
At the end of the day, the nice thing about the quick and dirty ways is if there is one, they make a lot more sense.
Yeah. And so hopefully this enlarges your bag of tricks. Now, in a complex case, because the question was, show that it's not in a product, and it basically boils down to, for the definition of its bilinear form, there's no conjugation. But so the easy way to show it is, so for C2, use an example that's complex. For example, V1 and V2 being purely imaginary. And you can go ahead and work this out. Like for instance, easy example would be like V1 equal to I. And so then you choose V2 to cancel this out, you get a negative result when you square it. So, I saw some explanations that were just talking in general terms. When you're trying to show that something is not true, cook up the simplest specific example that you can. And again, it's game over when that happens. Okay. Any questions about number 1 or number 2? Well, generally things got better after that. Well, okay. Number 3 still requires some commentary. Because I gave a formula for the orthogonal projection, which you all used. But you have to keep in mind the particular subspace you're dealing with. In this case, V0 was the subspace of constant functions. Now, my definition of my formula for orthogonal projection had to be very general. We're working with whatever subspace and therefore whatever orthogonal basis it has. But some subspaces, like the one in this problem, are a lot simpler than that. V0 in this case is a span of 1. There's a basis with one element in it. And many of you were just working with an infinite basis. And at some point, and for some of you, I did not have confidence that you understood that this is a one-dimensional subspace. That idea is essential, because that's how you know, oh, you only have to work with this. Or if you want to use the notation that I gave, work with E1 is equal to 1. There's no infinite sum here. Like some we're working with, E1 equal 1, E2 equal 2, and so forth. That's not a basis. It is a span of those, but a basis, like if we're getting to essential linear algebra concepts here, that elements of basis have to be linearly independent of one another. In other words, there's no redundancy. So know your subspace. Can it be described using a basis of just finitely many elements, or maybe just one? Like for example, polynomials of degree up to n. You can use n plus 1 functions to describe a space like that. So I was looking for your solution to see, do they seem to understand that there's only one element in the basis? And sometimes I had less confidence than for others. At this level, exposition is very important. Or even at a slightly lower level, as Dr. Schroeder teaching real analysis, and that class, once again, is a bloodbath of because students don't know how to express themselves mathematically. And it's a very proof-based class. Okay, so...
See, but all we need is to have a complex analysis again, and then real analysis will start being a nice class.
Okay, that's an interesting approach.
Well, it's just all relative.
Flogging will continue until morale improves. Well, next time we discuss the curriculum, we'll keep that in mind. Okay. Well, it has been several years since we've offered complex analysis. Okay. Other than that, things went quite well. There's certainly problems 4 and 6. I think everybody got those. On problem 5, the computation part, like showing the series is equal to this, that went well too. So the thing about number 5 is you're dealing with a function x cubed on minus pi to pi. There's a discontinuity when you extend it in intervals of 2 pi. So the graph looks like this, and then it repeats itself. So at each point of discontinuity, you look at the average. So f at any interval, any multiple of pi is equal to 0. So the Fourier series is equal to 0 because it's the average of the two values. And so it's because of that, what happens to the Fourier series for a function of jump discontinuities. And that's the main thing I'm looking for, so why it behaves like that. Now, you can also look at the Fourier series itself and see, you have sine of k pi for k equal 1 to infinity, which is always going to be 0, and conclude 0 for that reason. Which is fine, because I'm just looking for some explanation as to why it's equal to 0 there, or also why it disagrees with the original function. But the main thing to take away from that problem is when you have these jump discontinuities, the Fourier series converges to the average. Okay. So, so that's the story of the test that took forever. Okay.
So now we all.
So after I clicked errantly, we're back. Okay. Yeah, honestly, I forgot what the percentage of is a midterm. Okay, I have a site always up and.
Well, I see homeworks are 30, midterm is 30.
Oh, okay.
And final exam is 40. So.
Okay. So with the average being 87, that means that on average the class has lost 4 points towards their overall grade, which keeps everyone in the running for an A. Still. Now, because I've had to make some adjustments to the schedule because I'd budgeted just one class period for the test. So we're not going to see Chapter 6 after all, Dobuchi's wavelets. Hopefully we can still get through Chapter 5. So we'll still see some wavelet material. Rest of today and next week and getting into the discrete Fourier transform. And I'm not sure we're going to do homework problem-wise. Because from this set of notes, today I'm starting section 3.1. I only have 3 pages of notes for that. But that's fine because I spent time talking about the test. And then I'll continue with that section on Monday. And I looked for homework problems in this section, and I only found one that I really wanted to give. I'll find more from the rest of the chapter. But a lot of the problems from Chapter 3 so far require using MATLAB. Now, I believe everybody in here has a certain amount of MATLAB experience.
Yeah.
Or do you? Okay, yeah. All right, that's good, because I've given everyone else in this room lots of MATLAB work. All right, so that's something I can consider when choosing other homework problems. But okay. Oh, geez. Okay. So. So I guess yeah. So the next homework. Okay. So we have homework due on Monday for okay. So I need to refresh my memory on all that. Okay. Let's do it first. I looked at this. Oh, Chapter 2 stuff. Now, how's the Chapter 2 homework going? Or are people not really touched that because of a test?
Well, I believe the 2 and 3 are submitted.
Or what?
I believe I've submitted 2 and 3.
Well, and 4. I'm talking, yeah, homework. Okay, I don't know if you're talking about. Oh, chapter this number.
Oh, yeah, chapter.
Yeah. Because homework 2 and homework 3 both dealt with chapter.
Yes, chapter 4. Yes.
Yeah.
Homework 4 is submitted. Yes.
Okay.
So hopefully it's not as crappy as
Okay.
certain other.
Okay. Well, I still have homework 3 to grade, so now that the test is out of the way, I can get on that. So I guess we'll see how things are going. Chapter 2 homework probably on Monday, the day it's due. So of course we all know by now how I feel about due dates.
But the due date has already moved once.
Well, yeah, stuff happens. Okay. Okay. So in that case, if there are no questions about anything prior, we could take a look at beginnings of chapter 3 on this incredibly tilty board.
Ugh.
So you got 2 midterms to recover from, or many of you.
Oh, we've all got tests to recover from.
Oh, yeah.
Tests to recover from.
Yeah.
Dr. Dang's class is wonderful, but he believes, like you do, in giving real tests.
Okay. Interesting.
Well, to be fair, I wouldn't have expected anything less in a 7.
Oh, yeah. Okay. Alrighty. Now, if I have an integral from a 0 to pi, just any old function, and we'll scale it by 1 over 2 pi for convenience. So this is a kind of integral that pops up for a Fourier series, where you may have just the function you're taking a Fourier series of by itself, or it might be multiplied by a sine or a cosine. So we'll look at all those cases momentarily. But just in general, when you have some integral like this, an easy way to approximate this integral is, all right, so keep 1 over 2 pi, and then the integral itself, I have 2 pi over n, and then 1 over 2 plus y1 plus y2 all the way up to y minus 1 plus yn over 2. Okay, I need to define what these y's are. So each y is the function f evaluated at equally spaced points in the interval 0 to 2 pi. So the spacing of these points is h, which is 2 pi over n. So h is what goes here. All right. And so we take the interval 0 to 2 pi. And we have subintervals of equal width h. So y naught is valued at 0, yn is valued at 2 pi, and then we have values at points in between. Okay. All right. Now, the reason why we can say that this is an approximation of the integral is this is based on a numerical integration technique, the composite trapezoidal rule. Okay, because what happens with trapezoidal rule, what's the formula for the area of a trapezoid? It is the average of the heights times the width. Well, the width of each trapezoid is h, and then for the height, we get the height from the y values. But at the interior points, those are shared between 2 trapezoids. So that's why we don't have an over 2 here, because we have 2 of them that combine. Little trivia for you, that composite trapezoidal rule is also known as, I believe it's like the improved ties method. After a biologist, I think Mary Ty, who happened to invent the composite trapezoidal rule, not knowing that it had been in existence for over 100 years. But biologists, they're not going to know any better. I'm not sure what method it was an improvement of, might have been like something really simple like a Riemann sum. But she needed to approximate area under a curve, and so she was very pioneering. So that name actually got officially attached to this method, maybe to give mathematicians a laugh. I don't know. Okay, now let's suppose further that f is 2 pi periodic. Well, in that case, y naught is equal to yn. So now, and things simplify because we have these 2 pi's canceling. So, and also, since we're integrating over 0 to 2 pi, but we're dividing by 2 pi, this is the average value of f of t anyway. So it makes sense that the average value of f on the interval 0 to 2 pi can be approximated by taking the ordinary average, just the mean of the values of f at equally spaced points. Okay. All right. Now, so now I want to apply this idea to compute complex Fourier coefficients, where we have a more specific integrand in mind. So alpha k, each complex Fourier coefficient, is of this form. So 1 over 2 pi, integral from 0 to 2 pi. So in place of big f of t, we'll fill in little f of t, e to the minus ikt dt. So now we'll just apply this approximation. So we have approximately 1 over n sum, and we'll have f, little f, at equally spaced points, 2 pi j over n. So just I'm using hj where I've actually filled in the h. And then we also need the exponential. So e to the minus 2 pi ijk over n. So alphabet soup here. Now, the 2 pi j over n comes from the t, because they're equally spaced t values. And the I and k come from here, parameters of the function itself. Okay. Now, I'm going to write this using some shorthand here. So the f values, I'll call them little y's. And then for the exponential, we can refer to that as w conjugate to the jk power. So each little y is an f value at the equally spaced points. And then w is e to the I theta, where theta is, again, one of these equally spaced t values. And a reason for the conjugate here is because we have e to the minus ikt, which would refer to a complex conjugation. I didn't want to include the conjugate in the definition of w. Okay. All right. So if we go ahead and evaluate our function at these equally spaced points in 0 to 2 pi, and then we compute these this exponential, evaluate that at the same equally spaced points, then this expression will give me each one of the complex Fourier series coefficients. So this is the approximation that we're looking at here. Okay. All right. So now I can use this to formally define the discrete Fourier transform. For approximating Fourier series coefficients. Okay. So I'll define Sn. Now, in other classes, Sn refers to the symmetric group permutations of numbers 1 through n, but not here. We don't touch that here. So this is the so all n periodic sequences of complex numbers. So the sequence itself is infinite, but the numbers will repeat every n. Okay. So I'll let the sequence y, that's defined to be complex numbers yj. So this would be some n periodic sequence. Then the DFT, because it'll be aggravating to keep writing out discrete Fourier transform. The DFT of y is denoted by y hat, like we've seen before. We've used this notation with the continuous Fourier transform. So this also is a sequence. So each term of his sequence, and we refer to this as, so use a fancy f, with a subscript n to indicate this is an n-point discrete Fourier transform, because it's n periodic, applied to the sequence y. Now, one thing that's kind of aggravating when I was looking at the book is that I got this notation from the book, and yet in many cases they would drop the subscript n. And I didn't see an explanation as to why they do that. Maybe thinking, oh, it's like obvious from context or something. But I prefer to leave it in there so we know exactly what kind of discrete Fourier transform we're dealing with.
So is that a hint that we have a difficulty with understanding context?
No.
Oh, I'm just making a joke.
Okay. Yeah. Well, I don't go for subtleties because that just goes over students' heads anyway. Even at this level. Okay. So each element of this sequence, so the transformed sequence, I'll call it yk hat. So it's just this approximation here. Okay. So we have yj, so from our original sequence, and then we have w conjugate raised to the jk power, where w is again e to the 2 pi I over n. All right, so that's how we define the discrete Fourier transform. And, okay. Oh, sorry, I goofed. That 1 over n should not be there. So the official definition of a DFT, we're not using any scaling factor. However, if we do include the 1 over n, we can say that alpha k is approximately 1 over n yk hat. So this is very important. This is a relationship between the complex, so the exact complex Fourier series coefficients. If you're working with little f of t and actually evaluating the integrals like you have been doing in many other problems, even on the test, and the approximate coefficients that you can get from a DFT. So, and actually, this is so the way I have it here with no scaling factor is consistent with like if you compute the DFT in MATLAB, like using its fast Fourier transform function. I will talk about the fast Fourier transform soon. That they have no scaling factor here. So you just have to keep in mind this relationship if you're really trying to approximate Fourier series coefficients. Okay. Now, one thing that's nice about the DFT, speaking of MATLAB, is that you can view this computation of DFT coefficients and therefore approximate Fourier series coefficients as a matrix vector multiplication. So if now the sequence y is n periodic, so we only need to focus on like y0, y1 up to yn minus 1, and similarly y hat is also n periodic, so we only need to focus on n select elements from it. So if we think of y and y hat both as being represented by vectors of n elements, then we can go from one to the other by a matrix vector multiplication using a matrix of a nice structure. So I'll show you what that is. So I'm going to get slightly freewheeling with notation here, just for convenience or maybe laziness. So let's think of y as a vector consisting of elements from my n periodic sequence, y n minus 1, and then y hat is defined similarly. These are both vectors in Cn. Then I can say that y hat, if that is fn of y, so the discrete Fourier transform, can be written as, so here I'm going to use a non-fancy fn. So really it's the complex conjugate of this matrix Fn, where Fn is easily defined in terms of the complex number W that I have over there. So first column is all ones. Then we have powers of W starting from 0, so 1 W squared up to W n minus 1. Then we have powers of W squared. And then if I continue, it's like powers of W cubed, W fourth, and so forth, all the way down to the end, where you have powers of W to the n minus 1. So the very last entry is W raised to the n minus 1 squared power. And you guys can see it on the board, but someone who's watching can't see on this portion of the board, so I'll repeat. So W is e to the 2 pi I over n. So once you compute this, then you can easily define Fn. So then you can multiply your function values, your equally spaced function values, by this matrix Fn, and bam, that's your DFT. So conceptually, the simplest way to do it, although it's not very efficient, because for n coefficients, a matrix vector multiplication will take order n squared arithmetic operations, and we can do better than that using the fast Fourier transform, or FFT. But it's good to have this, to have an understanding of how the DFT process works. Okay. I should mention that this matrix Fn, the structure that it has, like the patterns you can see in the various numbers, that is a particular type of matrix. Does anyone happen to know what that is? Given the fact that we, like you think of each column as being the select set of numbers raised to appropriate power. And that power keeps increasing as you go from left to right. called a Vandermonde matrix, or this is an example of a Vandermonde matrix. There's more to it than that because not only because the numbers that are being exponentiated all have a pattern of their own right. Because the Vandermonde matrix, you can have any n x values. And there's no particular pattern to them. And you can have ones in the first column, then those numbers squared, cubed, and so forth. So there's at least a definite pattern to the columns, less so to the rows. But here we have it going both ways. All right. All right. One page down. Okay. Now, some properties of the DFT. Okay. So first of all, that the discrete Fourier transform operator, Fn, maps, so we know it as its domain, all n periodic sequences. But the result, I've said this, but I haven't really proven it, is that the result of the discrete DFT operator is also an n periodic sequence. So Fn is a linear operator on the space Sn of the n periodic sequences. Now, the linear part, not really interesting. I mean, you could basically be showing that you have two sequences that are summed together. You can either take the transform individually and add them, or you can sum them first and then take the transform and get the same result. And that just comes from the linearity of summations. Yeah. And similarly, if I multiply my n periodic sequence by a constant, I can then the DFT is multiplied by the same constant. But the part that's more interesting is, but even not much so, is the periodic part. You can show that if I have yk hat, that is equal to y hat coefficient k plus n. So that's what shows the n periodicity of the DFT. So just for fun, I'm going to show that. It's fun with complex numbers. So yk plus n hat, using the formula for DFT I have over there, so that would be sum j equals 0 to n minus 1, yj, and then I have w conjugate to the j k plus n power. Now, at this point, I'm going to fill in what w is. It's e to the 2 pi I over n. Notice that for y values, that part is exactly the same as what we'd have for yk hat by itself. So it's a w part that's, okay, so we have e to the minus 2 pi I over n times j times k plus n. Okay. So just filling in the definition of w and taking a conjugate there. All right. Now I'm going to break this up. Sum up to n minus 1. Okay. So I want to take the... Now this part is what I would have for just computing yk hat. So this is just w conjugate to the jk power. Well, it seems weird to be using jk, considering its colloquial meaning. But that's what you get for dealing with these letters very often. And then the rest of it is e to the minus 2 pi I j over n times n. Well, the n's cancel. So now we have e to the 2 pi I raised to the minus j power. Well, can anyone tell me what e to the 2 pi I is equal to?
So 1, isn't it?
Yeah. So e to the I theta, where theta is an integer multiple of 2 pi, is equal to 1. So all of this is equal to 1. So, and everything that's left is yk hat. So that establishes the periodicity. So any questions about what happened there? Okay. All right. Now another property. I'm doing on time here. Okay. Still plenty of it. It's about the relationship. So we have an inverse DFT. So you can go from y to y hat, but what about going from y hat back to y? Turns out that the processes are very similar. Okay, so another property, besides being a linear operator, is that if you have y hats, here's rewriting a definition of DFT. I want to put the two side by side, the transform and its inverse. So now y, you can recover y as the inverse transform of y hats. So for going back, you need a 1 over n. And you'll have a similar sum. It'll go from k equals 0 to n minus 1, yk hats. And then we have, w to the jk. So really what I should do is, okay, my notation in the notes is not that good, so I need to fix that later. Okay. So here I have yk hats. So I'm taking the kth element of a transform. Here I'm computing yj, so the jth element of the inverse transform. Because when I write fn of y, or fn inverse of y hat, that by itself refers to the entire sequence. But I'm only interested in expressing one element of these sequences. And if you look at these sums, very similar. You just have whatever sequence you're transforming, sum from 0 to n minus 1. You have w here, w conjugate here, both raised to the exact same power, jk. It's just that the inverse, you got to have a 1 over n, just for everything to work out. And now, what? I'm gonna to show that this is true. It's easiest to express both of these as a in terms of matrix vector multiplication. So okay, so we have y, which is Fn inverse of y hat. So now we're just working with a vector form that I have over there, and that is equal to 1 over n Fn of y hat. So Fn is the same Fn that I have over here. But the thing is, what is y hat equal to? Y hat I wrote over there. That is Fn conjugate times y. So what I'm saying is, if I take y, multiply it by Fn conjugate, and multiply it by Fn, and take 1 over n, I'm back where I started. So you need to show, to prove this, that 1 over n times Fn conjugate is equal to the n by n identity matrix. So if you can show that, then this property would be proven. Now, so to prove this, note that Fn conjugate is the same as Fn Hermitian transpose. Now, Hermitian transpose is transpose and complex conjugate. In other words, this matrix Fn, it's symmetric. When the matrix is complex, we tend to say complex symmetric, just to emphasize that it's complex, because a lot of properties that hold for real symmetric matrices do not generalize to complex symmetric matrices. You really want to go with Hermitian in that case, and remember to conjugate. But the fact that this matrix is symmetric helps us. So, so really what I'm saying is, I need to show that 1 over square root of n Fn is a unitary matrix. Now, what is a unitary matrix? Unitary matrix is the complex analog of a real orthogonal matrix. Now, orthogonal matrix, you multiply it with transpose and you get identity. So here, in other words, what I'm saying is 1 over square root of n Fn, 1 over square root of n Fnh, which is the same as 1 over n Fn conjugate, which is what I have over here, must be equal to identity. So if you can show that the rows and columns, actually it'd be enough to show the rows or columns of Fn form an orthonormal set, then you're done. That would prove this. All right. So that's what I'm going to do. I'm going to show that this is equal to identity by picking out a row of this matrix and a column of this one, and show you that you get ones from a diagonal and zeros otherwise. So what I'll do is I'll look at 1 over square root of n, Fn, 1 over square root of n, Fn Hermitian transpose, Ij. So that would be, I'll just combine the 1 over square root of n, so we get 1 over n out front. And then I have sum for, looks like I have a, oh, okay. Sorry, I need to be more consistent with my notes. The Lj entry, and that would be a sum k equals 0 to n minus 1. This is an entry of a matrix-matrix product. So from this matrix, I'm going to get w to the lk power. And then from the other matrix, I'll get w conjugate, because we're transposing and conjugating, to the kj power. So this comes straight from the formula for matrix-matrix multiplication, is what we get here. Okay. So now, to see, I want to show that this is equal to 1 if L equals J and 0 otherwise. So I'm going to fill in the definition of all these. So we have e to the 2 pi I over n lk from this one minus kj for this one. Okay. Now the k can be factored out. Here we have L minus J. Okay. Now, if L equals J, that's the easy case. Because then we just have e to the 0 here. And we're adding up 1 n times and dividing by n. So that'll definitely give us 1 if L is equal to J. On the other hand, if L is not equal to J, so really we're, due to periodicity, what I could say without a loss of generality, so for the L not equal to J case, is e to the 2 pi I, and I'm going to fill in some integer m over n times k, where m is equal to L minus J. So that's just some integer. That technically could be anything between like plus or minus quantity n minus 1. But the thing that's essential here is that it is an integer. Now, just the easiest way to show that this has to be 0 in this case, because what I could do is, alright, probably the best way to do this, since we're starting from 0 to n minus 1, this is, so it's this whole number raised to the kth power. That's a geometric progression. And we have a formula for the partial sum of a geometric progression. So I'll have a 1 over n, and then I'll have 1 minus e to the 2 pi I m over n to the n power. Because we're going from 0 to n minus 1, but now we're going to have n. And let's not forget the k. Well, actually, no, but the k goes away, we have n. Over 1 minus I m over n. Okay. Now, up top, the n's cancel. So we have e to the 2 pi I, which is 1. So numerator 0. We have to be certain that the denominator is non-zero. Keep in mind that, we don't want to have a 0 over 0 situation. But m is a difference between L and J. And so L and J are integers between, well, if we index like we're indexing everything else, between 0 and n minus 1. So we just don't want to have a situation. So we don't have a situation where L and J are not equal, but also L and J cannot be, like the difference between L and J cannot be an integer multiple of n, or we'd have a problem. But with those integers both being in this range, that's something that isn't going to happen. The result could be negative, but it's the difference between the two is not going to reach n or minus n. So therefore we can confidently say that this is going to be 0. So this matrix is identity. Therefore, that really is the inverse. So it proves establishes the validity of these formulas. Okay. So questions about what happened there? Which is quite a bit. Okay. Okay. All right. So now that we have that, may not even get through these 3 pages. Okay. I do have more properties for you. Okay. 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 So shifts of translations. So let's suppose that we have 2 sequences, y and z, that are n periodic sequences, and one is a shift of the other. So zj is equal to yj plus 1. So we're shifting all the elements of y by 1 to get the elements of z. Then there's a simple relationship between the Fourier transforms, the DFTs of y and z. So if I look at so you think that it's really zk hat is equal to Fourier transform, got my subscript, whoops, and we just multiply by w to the k. So that would be w to the k yk hat. And this can be shown just by applying a formula for the DFT directly, that if you just replace, computing the DFT of z and you fill in yj plus 1, then using the periodicity of the sequence of y values, you can show that this factor of wk is what gets factored out of the sum. Okay. Okay, so that's one property. Second property deals with convolutions. So we see convolutions for functions. We have convolutions of n periodic sequences also. So that would be a sum, and we have yk z to the j minus k. So this is a formula that's analogous to the formula for convolution of functions. In fact, that's defined by an integral. You have like f of t, g of x minus t, or something like that. And if you approximate that integral for convolution of functions by like a quadrature rule, like the positive trapezoidal rule, you would get a sum basically like this. So it's a natural definition. And the convolution of two n-periodic sequences is also n-periodic. So that's something that can be shown. Similar to how I showed that the DFT itself is periodic. And you have the same simple relationship between convolutions and products for sequences as you do for functions. So if I take a convolution of two n-periodic sequences and then take its DFT, that's the same as taking a DFT of y and z individually and multiplying them together. So this is a convolution theorem for the discrete case, which is just like a convolution theorem for the continuous case. So transform of a convolution is a product of the transforms. Okay. And another property is that if I have there's a certain symmetry, kind of, with the DFT coefficients, that if I take a particular DFT coefficient and take its complex conjugate, that's the same as if you reflect the index across the middle of your indices, so n minus k instead of k, then you get that coefficient. So there's that nice symmetry to that. Okay. All right, what to do at this point? Because I only have 15 minutes left. All right, what I'm going to do, that's right. I've only picked out one homework problem so far. It's number 2 in chapter 3, which I want to refresh my memory as to what that is. Because I don't want to have something where I do something on the board and realize, oh, that's a homework problem.
Oh, please.
Yeah, because that's never happened before. Oh. Why won't it let me search for files I've opened? It drives me nuts when they update applications and take away features that you were really making heavy use of. Okay, if it just move things around, because you always act like a user doesn't really know what they want. Okay, so chapter 3. Exercise 2. Oh, okay. It's to prove one of the theorems. Okay, which theorem? Oh, theorem 3.4. I just want to look at which one that is. And hope I didn't do it already. I might have, by mistake. Oh, I have not. But I almost did.
Oh, darn.
So the only exercise I give in chapter 3 so far, number 2, all these properties are condensed in a theorem, theorem 3.4. The exercise is simply to prove all this. And I was going to pick out one of them and do it to kill the last 15 minutes.
Darn.
So I almost accidentally did some of your homework for you. So, but you get to have your own fun of complex numbers, just like I did earlier. So, yeah. Okay.
We'll put all that complex analysis to use that we'll have to have learned on our own.
Well, I guess you did have some problems from one of the previous homeworks. Yeah, that I kept referring to as complex number fun facts. So, okay. All right, but I think, yeah, I don't want to just rush through FFT or have it cut off in the middle. So Monday, I'll cover FFT. Apparently there's some outrage at that suggestion.
I cannot imagine that any. I don't know how to continue.
Okay. Well, on that note, yeah, let's stop here. Ooh, I got through 2 pages. Woo.
Well, it's just we're out of practice.